A father wants to share his inheritance between his two children. The inherited assets are stored in a safe, which requires a 4-digit code to be opened. However, the father did not want his two children to fight over the property, so he decided to give two different clues or information to each of his children so that they could only get the code to open the safe if and only if they work together and combine the clues or information they had. So, how does he do it? First, let me introduce myself. My name is Muhammad Gian Gymnas alim. I'm from Hasanuddin University, Indonesia. So, in this video, we'll discuss about Shamir's secret sharing with the finite field concept to solve the previous problem. The simplest approach is to give the first 2-digit code to the first child, then the last 2-digit code to the second child. Thus, they both have to exchange information if they are required to open the safe. That is a simple example of secret sharing, where in this example we split the information to two people. But there is another problem, which is one of them can just brute force the safe because they just need 100 more tries to open the safe. Of course, they can easily open the safe within a few minutes. Now let's look at this simple observation. If we have one point on the graph, there is an infinite number of straight lines that pass through this point. Each of these lines intersects the y-axis at a different point. However, if we have two distinct points on a graph, there is only exactly one line that passes through both points, and this line intersects y-axis at a unique point. From here, we can now implement the secret code as the intersection point between a line and the y-axis, and then partial code as two distinct random points spread on that line. But in order to achieve correctness, that is, if you have two shares of the secret, you can uniquely determine the original secret value, and perfect secrecy, that is, if you only have one share of the secret, all values of the secret are equally likely. We need to work on a field. Why? First, let's recap what is the definition of a field and its properties. A field is a set with two binary operations called addition and multiplication. These operations are required to satisfy the following properties. First, you want addition and multiplication to be commutative. That is, it should not matter when you add A to B or B to A, the resulting number should be the same. Second, we want both operations to be associative. It should not matter when you first multiply A and B, and then multiply by C, or whether you first multiply B and C, and then multiply by A. Next, we require that there be a so-called identity elements for each binary operation. We will need this in order to define the inverse elements. We require that there are two distinct numbers 0 and 1, so that for any number if you add 0, you get the same number back, and for any number if you multiply by 1, you get also the same number back. We can then define what we require of the inverse values. For addition, for every number A, there exists an additive inverse value, negative A, so that if you add these elements together, you get the identity element of the addition operation, which is 0. Similarly, for multiplication, for every number A, there exists a multiplicative inverse value, A to the power of minus 1, so that if you multiply these elements together, you get the identity element of the multiplication operation, which is 1. As you already know, there is one exception here, namely that we don't require that there exists an inverse element for multiplication for the identity elements of addition. There is a very complicated way of saying that there doesn't have to be a number which you could multiply by 0 and get 1. Effectively, it is the same as saying that division by 0 is undefined. Finally, there is the somewhat more technical property of distributivity, which explains how the addition and multiplication operation combine. Besides these algebraic properties, Shamir's secret sharing usually implemented over a finite field. There is a field with a finite set, because finite fields enable efficient arithmetic operations, making them suitable for cryptographic algorithms and error-correcting codes. One way we can construct a finite field by create a set of finite integers with modulo operation that is set P, where P is a prime number. I won't explain why ZP form a field in this video to save the time. We can now back to the problem and implement this concept. Because the safe requires 4-digit code to be opened, we need at least 10,000 elements in our field. We can take set 10,007 because 10,007 is the smallest prime number that is greater than 10,000. Let's say that the code is 2473, so we construct a function f with the domain set 10,007 and the range is also set 10,007. Fx is equal to 2473 plus bx modulo 10,007. Let's choose b is equal to negative 267, so our function is fx is equal to 2473 minus 267x, and the secret code is f0 is equal to 2473. Now, the father can give another 2 points to his child. Let's say the first child learns that f1 is equal to 2206, and the second child learns that f2 is equal to 1939. Therefore, if the first child only knows his point on the line, he doesn't learn anything about the possible value of the code. And same thing happened with the second child. Only when they combine their information, they can use basic high school math to construct a line and find the secret code on F0.